First of all, I'd like to thank the organizers for inviting me to give this talk. So, people have already talked about magnetospheric oscillations. So, in the morning also we have got a quite nice talk about planet-star interactions. So, it will be interface between these two. So, we're going to do some small scale to large scale, then to again to small scale. So, let us now talk about it. So my plan of the talk will be something like a magnetosphere, particularly arch magnetosphere, plasma oscillation, and an in situ observation. We are going to talk a little bit about that, particularly cluster sets of satellites. Then theoretical modeling of nonlinear oscillations, like what questions we can talk about. So we talk about the slow-move solitons of pressure modeling. Basically, pressure anisotropic equations comes here, and then aperiodic oscillations. And then we talk about the multiphase. We're going to some large scale. Of course, this is not a part of magnetosphere, but we'd like to show you how general the assumption of this pressure anisotropy model. And then we talk about the plasma debris interaction, because we come closer to the Earth, and we use the plasma debris interaction as a model for parameter discovery of the magnetospheric oscillations, because the low Earth orbit debris interaction essentially is a part of the magnetosphere. So then we do an inverse problem, that is the neural network, physics-informed neural network parameter discovery, which is an ongoing work. So I'll just outline the whole thing. So it's very simple. I am not doing a lot of mathematics for the benefit of the heterogeneous crowd. So the magnetosphere, the basics already we all know about it. This crowd very well knows, but this magnetosphere is basically composed of the bow shock, magnetoseed, magnetopause, tail lobes, and plasma sphere, specifically arch magnetosphere, and we exclusively use some data from the cluster satellites, which are 4 satellites flown in around early or mid 2000 by European Space Agency, and which have now retired, but the cluster data are very well preserved and one can access freely, and these are very well organized, and you can just using a Python code you can access the cluster data, and they contain the whole treasure of information, because cluster has a very elongated elliptical orbit encompassing geotail, magnetopause, and bow shock and kind of things. So these are a kind of example of electrostatic oscillation in geomagnetic tail, which are observed by NASA's IMP-7 spacecraft, which is a 1999 work, and you can see the blow-up form of the waveform of the electric fields that one in perpendicular direction, EY and EX, the two graphs that you can see here. So, and if you go a little bit more, then you can see the spectrum, like this is electric field, of course, electric field versus time, and then you have got the power spectrum analysis, and from this you can actually find out like what are the inside this oscillations look like. So then we have a little bit about the knowledge of the cluster spacecraft, where you can see it is very much in an elongated orbit, and it's a set of 4 spacecraft, and it also touches the bow shock and magnetopause, and it works on a geocentric solar ecliptic coordinate system, where the x-axis is from the sun to the Earth, and other two are orthogonal. And of course it has got a slight inclination to the magnetic axis. So because it's necessary for data analysis. And now we talk about the theoretical modeling of nonlinear plasma oscillations. Now I will be very simple, like electrostatic nonlinear oscillations. What kind of equations do you have at your disposal? So for example, in the Hall MSD framework, we have already talked a lot about Hall MSD framework. The simplest momentum equation, I am discarding the other equations for the benefit of the clarity. So we have got a momentum equation, then you have got an isotropic pressure gradient term, and where the pressure is given by that famous pressure equations. And of course, it's a single fluid model. We have got a single plasma density. It's a Hall current term. And we have the ubiquitous equations then people generally use for as an equation of state is the CGL set of equations, which are double adiabatic equations, and which actually says that these two pressures evolve quite independently. The parallel and perpendicular evolve completely independently, because only on that limit you can derive CGL equations. And in the cartoon picture of that, if you have a flux tube and you have a point P1 and P2, this is of course from the Kulsrud, the famous handbook of plasma physics. And this P1 and P2 are completely like unconnected information, because the parallel and perpendicular length scales are completely out of pitch. I mean, one is very large and one is very small. But if you do a slight scale calculations in the different regions of the magnetosphere, then you can immediately see that the CGL equations are completely violated to a great degree. Like these parallel length and perpendicular length ratio comes out to be around 0.1 to 30, for example, in the magnetotail or plasma seed, which doesn't qualify that CGL equations can be used. So that Stasiewicz has, proposed a polybaric pressure, which is actually address the plasma anisotropy from a single parameter point of view, that is called AP. AP is the anisotropic parameter, which is like a ratio of the P parallel to P perpendicular -1, and P perpendicular is like a polytropic pressure, which is a density to the power gamma, magnetic field to the power kappa, which is a kind of a, you can adjust gamma and kappa coefficients indices to adjust the pressure. So if you use that equation and then try to do a Hall MSD model with this model, then you ultimately can reduce, after some mathematical reductions, you can reduce to two dynamical equations, a By and Bz, in that coordinate system that we have shown you for the cluster data, that x is toward the earth and other two axes are perpendicular to that. So that's By and Bz corresponds to those two perpendicular quantity. And if you look at this, the left hand graph is a real cluster data in real time, and the right hand is a production of the solution of the equations of those equations that we have seen in the earlier phase. So you can see that they very well corroborate the magnetosphere modeling. That's a strong indication that anisotropy can be addressed in the magnetospheric region from the point of view of a single parameter. If you go further, if you look at the different magnetospheric oscillations, you not only see solitons, you also see a train of solitons which are like a decreasing or increasing magnitude. I mean, like, for example, aperiodic oscillation, that we call it aperiodic solutions. And this is a work we did with our PhD student back in 2019. And this is a real cluster data reduced from the left-hand side. And these are also cluster data plot from the experimental plot. I draw your attention to the blue curve that is a actually magnetic field oscillation. As you can see that these are actually supposed to be solitons because they are actually time frozen. I mean, like, you know, they are like they're moving with the time. So, but their amplitude are increasing. So we say that we can probably model this with a, one question was that why the electron pressure was there. This is actually finite Larmor radius term. If you work out the generalized Ohm's law, then you can find a lot of terms on the right hand side of the first equation, and many of the times are neglected, but here we have kept the Hall current term and the finite Larmor radius term, that is the electron pressure gradient term, and which if you do the recalculate this, then you can reduce the equation after some calculation to the new set of equations, dynamical equations. Again, the coordinates are same, By and Bz, and you can actually do a nonlinear low dimensional dynamical analysis to see that this actually gives rise to those solitary structures with increasing and decreasing magnitude. And if you try to put it the actual parameter regime, then you can see the left-hand side is where there is no FLR term or finite Larmor radius term. The right-hand side is a with FLR term, and the region that is marked with colored diagram is the region where the linear oscillations are allowed. The other parts are nonlinear oscillations. So that means the regions are completely different. And now if you take the left-hand side, the real cluster data, right-hand side is our modeling of those oscillations, and we could up to quite a fair degree, we could model these oscillations with real experimental parameters, and that suggests strongly that FLR, finite Larmor radius effect in the magnetosphere should be taken into account in very many calculations. That is one thing. Now, if we just want to say that this polybaric addressing the pressure anisotropy from the single point of parameter, we can extend even to the large-scale interstellar matter simulation, which is a very recent work, just came out in MNRS January. So this is actually what we have said, that you do a again Hall MSD model, but with a supernova forcing term, FSN, that's a supernova forcing term. It's actually a large scale, and you have got this radiative cooling term, that is rho L, the curly L, you can see the second equation. And if you work out the interstellar evolution of the interstellar matter, you get some interesting results, and these are density maps, like a density concentration. These are not gravitational, these are rather thermal, and you can see that these are 2D simulations, and you can see that the pressure anisotropy, it doesn't play a huge amount of part here. So that's an interesting point. Earlier, if you take CGL equation, your pictures are quite different if you take different pressure anisotropy. But here, you can see up to only a slight variation of density fluctuation after around 850 million years, you can see the interstellar matter. So that's interesting. It's a kind of a null finding, but it's interesting. This paper just came out in January in MNRS. And this is the distribution of the warm neutral matter and cold neutral matter and unstable neutral matter. You can see that this makes a little bit of difference, where you can see that AP, the anisotropic parameter, is 3 for beta, plasma beta at about 5, which is a standard kind of these things. Now we go to near Earth. Now our idea is to, if we can decode the magnetospheric oscillations, that means if we can discover the parameters, different parameters that are required to explain different magnetospheric oscillations. 2 of the examples I have already shown you. So this plasma debris interaction provide a kind of experimental framework and plasma parameter discovery framework to do that. So that's what we have said, because this has also gained a recent attention, plasma debris interactions. That's to give a bird's eye view. This is a kind of debris picture, a real picture from the paper. You can see the number of satellites, which are blue color, and number of debris around the low Earth orbit, few 100 kilometers above. You can see the number of active satellites are around 11,700 active satellites. Debris mass consists of around 8,000 metric tons. And the most abundant are the 1 millimeter, that 128 million size, 1 millimeter to 1 centimeter small particle, which are undetectable virtually by any instrument. So the only way to know about their interaction with the ambient plasma. So that's why the plasma debris interaction has a lot of research going on. And this is from of course, a 2023 very recent paper. And you can see that this is a kind of proof of principle kind of things, that EPOP is an payload aboard the Cassiopeia satellites by European Union, and you have this Starlink satellites which are interacting with the low Earth plasma, ionospheric plasma, and generating a Mach cone, and this Mach cone can be detected, and you have a snapshot of that real data, and then this is the signature sudden hike in the signal, and you can see that inset pictures, that the Mach cone when it crosses the instrument, EPOP, Starlink interacting with the magnetosphere, then the interaction, the signature of the interaction is detected by the EPOP payload. So another satellite interacting. Now if you look at this, now this is another by interaction of the iridium, that is satellite phone, iridium 911 interaction with the low Earth orbit plasmas, and you can see that this is simulated ion acoustic wave for this particular interaction. This is a simulated ion acoustic wave from the same paper at 2023, and that one can one can see that these are kind of things which we can study by interaction of the satellites, smaller satellites like a box-sized satellites with the magnetospheric plasmas, or particularly low Earth. So this is the kind of satellite mission. The EPOP, the Cassiopeia satellite, is placed in equatorial orbit, very high. I think it's a geostationary, maybe 36,000 kilometers above or something like that. So now, so this is just for curiosity's sake. And that. Okay, now if you talk about the plasma debris simulation, or if you want to model it theoretically, then you come up with interaction model, which is, I am giving the bare minimum equation of the momentum conservation and the Poisson equation, because it's an electrostatic interaction, and debris is modeled as an external charge, which is given by rho tau external, which moves at a certain velocity Vd over the ambient plasma. And you have got a two fluid model. And of course, we have done this with a flux-corrected transport simulation, as well as we have a PIC simulation code also. Both of the codes are in-house coded. That means it's a generation of our own group. And we have not used any black box codes. Both are generated, those are 2D codes. PIC is still not, we are trying to make it 2D. And these are some of the results that you find out. The orange strip actually denotes the position of the debris, and the plasma is flowing like that, and you have got the generation of electrostatic waves. So these are maybe ion acoustic wave, maybe Langmuir oscillations. So, and this is work by one of my students in 2023 POP and physics of plasmas. And this is a recent work where we have shown that this, where you have seen that drop lines are longer means they are chaotic. So that means you can even see that these oscillations, the interaction of debris with the plasma, even they are chaotic depending on the velocity of the debris. So you detect a chaotic nature, and that work is by Bikramjit, and that's in the chaos soliton and fractals. It's a very recent, last year, 2025. And now we come to our last part of the things. How much time I have? Okay, fine, 6 minutes is good enough. So now I talk about, you perhaps know these two persons. These are, 2024 Physics Nobel laureate, John Hopfield and Geoffrey Hinton. And it showed you that the work is in computer science, but the Nobel Prize given in physics because it is inspired from physics like a, thermal Maxwell distribution law. So, but anyway, we are not going to do about that. But the thing is that this is what I have seen several posters also doing AI, so data-driven parameter discovery related to plasma physics. So we have taken the plasma debris interaction as a working model. Our intention is to uncode or decode the magnetospheric plasma oscillations. So this is a very preliminary work that is just going on. We'll just show you a very simple example from some of the work recently we have done. So this is an inverse problem. That means we don't know what equations to be used. We want to dictate the network to tell us which parameters are to be used, the parameter discovery. That means which equation I should use. For example, this is a earlier snapshot that I have shown you, that you have got a iridium satellite interacting with the low Earth orbit plasmas and generating a Mach cone detected by the EPOP satellites, and then you have got a representative pulse of that. That's a theoretical pulse. The right-hand side is a theoretical pulse generated by solving a KdV equation, Korteweg-de Vries equation. So this is the simplest Korteweg-de Vries equation for a plasma debris interaction. That's called force KdV equations. Now, you not only have the FKdV or force KdV, you can also have a force nonlinear Schrodinger equation. That is also one of the equations of nonlinear plasma physics. Not only that, you might also add a Landau damping term, a kinetic correction to the KdV equation, which is a fluid equation. You can do a kinetic correction to the fluid equation to add a Landau damping-like term, making the whole equation behave like a Berger's equation, which is like a viscosity damping. Not only that, you might have a more kinetic effect incorporating into the KdV equation, which is like a Summel trapped particle kinetic effect incorporated into the KdV equations. So references are there. One can go into that. Means the number of equations that you want to use to describe this magnetospheric oscillations are immense. It is only your own imagination that what term I should include and what term I should include not. So naturally a question arises that what equation to use and what effects should be included. So can your neural network process can help you decide what to include and what to not to include. That's the question. So everybody knows that this is a neural network which is thought to be an optimization. Basically, it's an optimization problem. Neural network is an optimization problem. And our idea is to set up the equation as an optimization problem. So solving a differential equation optimization problem. And this, I'm not going to details, but this is you define two residual function for the optimized, because you have to optimize something. One optimization comes from the initial and boundary condition. That means if you use a differential equation, put down the initial condition and boundary condition, equation should be satisfied. That means the residual should be 0. That is one. And the other equations that you can do is the network approximated potential or the variable and the real variable. If you subtract this, take a modulus, then you get the next loss function. So that means one loss function is through initial and boundary condition, one loss function is through optimization. Use the two loss function, put in a network, and solve with a high power machine, and you get your parameters. It's that simple as that. So use LPD as a trial, because that's an exact, because you put initial and boundary condition, equation have to be solved. And use this as a goal. So the trial and the goal, and you solve it, and you can detect. So this is a mathematical generated analytical solution of the equation that I have written above, with the parameters A, B, S naught. S naught is the strength of the debris, VD is the velocity of the debris, delta is the width of the surge distribution of the debris. A, B are constant. A is the coefficient of the time derivative, B is the coefficient with a nonlinear term. Now if I put into the network with this mathematical form, then I can, well, these are the, you don't have to know about, these are some of the things that we have used. And generate the FKDV solution, initial guess, then TensorFlow, auto differentiation.
Madhur, you have 2 minutes.
Yeah, sure, I have. So these are the pin architecture. These are the neural network architecture. There are two inputs, X and T. One output, this is a phi electrostatic potential to be determined. We have used, for example, a very modest hidden layers of 8, neuron layer of 50. Weight are standard, activation function standard, optimizer Adams, fine tuning. These are standard parlance in artificial neural network. And these are the value that is being discovered. So true value is 2. As you can see, the discovered parameters for this force KdV equation is almost on the dot. The network has been able to discover this completely by using the trial analytical solution. Now, the next one, this is the mathematical generated analytical solution, but we want to apply to this real data. Real data comes with a lot of artifacts, noise, other kind of things. So our first goal is to test these things with a PIC simulation data. So we have a PIC code in household PIC code where we have already benchmarked it. So let us, why not use the PIC code data to simulate that generation plasma debris interaction wavelength, and then try to predict whether we can do it or not. So that is the first thing, because PIC in a sense is more realistic than the analytically solved equation data. So we have got a PIC code. So this is a work from 2023. This is a representative pulse. It's a simulation by one of my students, Bikramjit. And this is a PIC, and you have to clean it by cleaning noise, because there will be some numerical noise. And then we put it into the network, and you can see, of course, to be modest, we have discovered on the 3 parameters. That is the S naught, the strength of the debris, the velocity of the debris, and the width of the surge distribution. And you can see that we are almost very, very close to the realistic value that has been used to simulate the PIC code. This is not equation solving, PIC code, and we have done that. So what next is the real satellite data. And we also plan to use the Aditya L1 data. Is my last slide. only one slide more. So Aditya L1 data, but Aditya L1, as an Indian, we are proud that we should use it, but there are lots of data gaps, and data are not properly structured. So we are facing difficulty in organizing the data. On the other hand, clusters is a very well organized data. So, but nevertheless, we hope that Aditya L1 will be able to give us some of the data so that we can catch some of the magnetospheric physics. And this is my acknowledgement. My Madhusmita and Hitendra, the upper two, have got all the PhDs. Those are Bikram's at the right-hand side working. And Diptarag is the recent recruitment as a PhD scholar. Thank you so much for your kind attention.
So what is the charging mechanism of debris in the plasma background? Charging.
Charge mechanism of the debris. This
The-
is just like electrostatic charging. It's a capacitive charging.
But there is magnetic field, so.
Yeah, there is a magnetic field, but right now we are not using the magnetic field.
But you are talking about the debris in magnetosphere, so there will be magnetic field.
I know, but this is a working framework. We say that we have used that as a test bed, and ultimately we'll expand this to the magnetosphere. Then of course magnetic field will come, and you have to maybe use higher dimension. Now it is a 1D work, but then you'll have to go to 2D and 3D also. But this will require a lot of computational power.
Yeah, 1 minute.
Thank you for this talk. I am Shishir Purohit from IPR.
Yes.
I'm really happy that you are using AI. So, very fundamental problem when we use experimental data with AI or neural networks, that we have to do some pre-preparation, as you mentioned.
What's that?
Pre-preparation.
Pre-filtration, yes.
Yeah. So, how much challenging it is with different data set? Because when I am doing it with our
How much what?
how much challenging it is.
Challenge, yeah.
Yeah. Because
Okay.
you know, for our tokamak business, you know, lot of different kind of or set of or family of frequencies comes into the picture,
Yes.
and which is oversetting to the real physics
Yes.
information. So, what kind of typical filtering or which kind of information you, don't want to see in your signal? What are typical information which you don't want to see in your
Right.
signal?
Yeah. Actually, let me tell you that we are yet to use a real satellite data. We have not used, we are on the process of using cluster data. We also want to Aditya L1 data, but Aditya L1 is having a data gaps. So we are using the cluster data. Right now, we are just trying to understand that. So probably your question will be answered after a few months. But it will require cleaning. It will require cleaning because you don't want to model those noise. Yeah.
Okay, one more question, yeah.
Hello, sir. My name is Vivek. I had a big question in the beginning of the presentation and about the magnetosphere. So you said you aligned your axis as X with the rotation of the Earth around the Sun, and then Y and Z perpendicular to that, right? So ideally,
This is the coordinate where cluster satellites work.
Okay.
Their data are available on this 3 coordinate
Okay.
direction.
And so the measurements from that, the BX and the BY are much smaller than the BZ, right? Like about 100 times less than the BZ values in the
Yes.
beginning. But if theoretically, if the magnetic north and south pole was aligned with the rotation of the Earth's axis.
No, it's not aligned.
Yes, it is tilted. But if it was, then we would measure BX and BY as completely zero, right?
Yes, yes.
So did you use that BX and BY numbers to predict the multi-phase ISM density plot you got in the end? So about that,
Don't connect your multiphase ISM to this multiphase ISM interstellar. Okay,
Yes.
that's a very, very large scale. That I have shown as how universal the concept of the anisotropic pressure, polybaric pressure model that we are using. That's not actually applied. We have not applied that multiphase ISM to interstellar, low Earth plasma, for which the cluster satellites are doing data. We have not concluded cluster data to multiphase ISM. Cluster data cannot give you multiphase ISM because these are only within the Earth magnetosphere. ISM is above
Outside.
that. Yeah.
okay, no, because my question.
I think
Okay.
we'll have a discussion
Okay,
later.
sure.
We can catch up. Thank you very much, Madhurya,
Yeah,
for a nice
thank you.
talk.